So I did receive a question from a student about coupling constants, and that relates to the splitting patterns or multiplicity that you see in NMR spectra. So we'll definitely talk about that. And we'll talk about, obviously, the other topics here from day 23. Let's get right into that then. So here's a spectra, an NMR spectra. I can tell, obviously, from the label here that it's a proton NMR. I can also usually tell the proton NMR because it runs from about 0 ppm to up to about 12. So clearly this is only showing a part of the spectra. There may not be any peaks above that. But the first thing I want to talk about today before we get into splitting patterns is integration. So as we were saying a little bit last time, if I have a structure and let's say my structure is ethanol. Each hydrogen in the structure, actually, let's go with this instead. So each hydrogen in the structure inside this magnetic field, it gets excited by the radio waves. Then when it relaxes back down, it releases energy, and that depends on what its surroundings are like. That determines the quantity of energy emitted. So if I have a couple of hydrogens here, which hopefully you recognize based on our discussion last time, these two hydrogens are equivalent. They happen to be enantiotopic. There's a plane of symmetry that makes them equivalent to one another. They have the same surroundings. So they're going to give the same signal. So wherever that signal appears, it's going to be representing this hydrogen and this hydrogen. And there also happens to be another plane of symmetry here, right down here, that makes these two hydrogens also equivalent. So here I would have 4 hydrogens producing the same, all the hydrogens would be producing a signal, but since they're equivalent, the signal for each of those would appear in the exact same position. So the signal for those 4 hydrogens happens to appear right here. There's also 6 hydrogens here on the structure. Due to this plane of symmetry or rotational axis of symmetry here, all 6 of these protons are equivalent. So they're still each giving a signal, but the signal for one of them would be relatively small. The signal for another one would be in the exact same spot, and it would just add to the size and or width of that signal. And then the next hydrogen would also give a signal. Eventually, all 6 hydrogens, all giving signals in the exact same spot, result in the signal increasing its size. So the number of hydrogens producing signals that are equivalent to one another, they don't necessarily always make the signal taller. They may make the signal wider, but they definitely make the signal have a greater area. So what people used to do before we had common access to computers is they would get a printout of the NMR on paper, and then they would cut out the peaks. And if they cut out this peak and measure the mass of it, and then cut out this peak, be careful to cut right along the lines, the mass of the piece of paper would relate to the area of that signal. The space or area of the signal or peak relates to the number of hydrogens producing that signal, right? So the more hydrogens I have producing a signal, the bigger the area or integration of the signal will be. So nowadays we don't have to cut that out and measure the relative mass to figure out the relative areas of the signal. We have computers that can do calculus, obviously, and they can calculate the area or integration of the signal And typically, when that's done, you're using a software that allows you to pick out exactly where you want the area to be calculated. So I would pick out this area in here, and it would calculate an integration for that. And then I would tell the computer here and here, here's where I want the other sections integration to be calculated. And the relative integrations would be shown with these little integral symbols. And then you have to tell the computer what the integration is for one of these peaks, and it will give you the relative integration of the other. So if one of these has clearly a smaller integral than the other, I could set this to 1, and I would find out that relative to that, this one comes out to about 1.5. And I would say, well, I can't have half of a hydrogen adding to that signal, so what I'm going to do is double this here and set this one equal to 2. And when that one's equal to 2, this one would end up being equal to 3. So that tells me it's a 2 to 3 ratio. Or for every 2 hydrogens producing this signal of this type, there are 3 hydrogens of this type producing the other signal. It doesn't necessarily tell me that there are 5 total hydrogens in the structure. It's really just a ratio or relative amounts of hydrogens because it's a ratio or relative areas or integrals or area under the peak. So you definitely want to be able to recognize that the area of the signal relates to the number of hydrogens producing the signal. And if you're given an NMR, be able to relate that to the structure of the molecule, as well as if I give you a structure, be able to determine what the relative integration should be for the peaks. Right, so let's take a look at this example. So here's one we didn't get a chance to look at on Tuesday, but we want to practice determining how many signals there will be, what the relative shift of those signals will be using the chart that's on the formula sheet, and then the integrations, which is what we're talking about right now. Right, so in this structure here, obviously, if I'm looking at the proton NMR, I would want to potentially draw in all the hydrogens. And there are a number on this structure here. Almost isn't even space to draw them all. Right, and everywhere where a line ends, there's a hydrogen. Enough hydrogens to complete the noble gas configurations. So there's no hydrogens on this carbon or on this carbon because there's already 4 bonds shown, obviously. So how many signals would this structure give in the NMR, proton NMR signals?
Would it give 3?
Yeah, so it could look like 3. However, here I would really only see 2 signals. And probably what you're not noticing is that all 9 of these hydrogens are equivalent to all 9 of these hydrogens because of rotational and mirror plane symmetry, right? So if I wanted to do a replacement test to help me prove that, I could replace any one of these 18 hydrogens with the deuterium. So I could just randomly do that. Maybe this one here. And then I could replace any other one of those 18 hydrogens with the deuterium randomly. And if I wanted to be really thorough, I would do it for all of them. And then I'd have to show that those 2 structures aren't different. Either that they're the same structure and identical, which would make the hydrogens homotopic and equivalent, or maybe they would be enantiomers, which would make the hydrogens enantiotopic, which would also make them equivalent and all give the same signal. In this case, they're homotopic. Right? If I flip the structure over and rotate this bond here, I can get this deuterium to line up directly on top of that deuterium. So through bond rotations or flipping the structure over, if I can show that atoms are equivalent and replacing one with a different element versus the other with a different element gives me either two structures that are identical or two structures that are enantiomers. That proves to me that all those protons are equivalent. So in this particular case, I would have 18 protons that are all equivalent. And I would expect, since those are methyl groups, that aren't near any highly electronegative atoms to cause deshielding. They're not near a pi bond. They're not near an aromatic ring. They're not near a CO double bond, a triple bond, an oxygen, or anything more electronegative than that. They're just plain old hydrogens bonded to carbons. And the methyl groups appear on the lower end side of that, which is why we have that here. Primary or methyl carbons and hydrogens aren't very deshielded, and they usually appear around 1 or just below 1. So we can call those all HA. It'll be around 1 ppm. And the other two protons that are different from those but equivalent to one another are right here, these two protons on this methylene. These two protons obviously are on a CH2, which makes them different from any of the ones on a CH3. But if I were to replace one with the deuterium, versus replacing the other with the deuterium, what's the relationship? They're homotopic. These two structures are identical. All I have to do is flip this over like a pancake, and the deuterium that's now pointing away will be pointing out front. The two groups, this group here will be equivalent to that one. It'll flip over and be superimposable right on that spot. This group here will be superimposable on this spot. So these two structures are superimposable, which means the two hydrogens that I did this replacement test for are homotopic and equivalent. And so they should give one signal as well. And since that's a methylene, it's a secondary carbon, it's going to be slightly downfield from the methyl groups, maybe around 1 to 1.5. So despite having lots of hydrogens, each hydrogen gives a signal. Because so many of them are equivalent to one another, I'm only going to see two signals on this whole spectrum, and they're going to be way down here close to 0. So I'm not even going to draw the whole spectrum. I'm just going to focus in, on the beginning of the spectrum here. I would expect to see a signal for all 18 of those hydrogens, and that signal would probably be much taller and broader. It might not actually be more broad, but it would definitely be taller. It would have a larger area for the signal. Actually, let me make that in blue so it matches the blue highlight there. And then the signal for the hydrogens in green would be a little farther up, right here maybe. So if I then tell the computer to integrate these signals and give me the relative area of the signal, so what it will do when it does the integration is it will translate the area into a height from here to here for this integral. So if I integrate both signals, I'll have an integral for that, and I'll have a much larger integral for the other one because the area under that signal is much larger because there's a larger number of hydrogens of that type, all producing a signal, adding together, making the signal larger and larger with a greater and greater area. So if I set this integral to 1, I would find this integrates to 9. Right, so it's a 1 to 9 ratio. Ultimately, it's 2 protons of this type for every 18 of this type. But if I do 18 divided by 2, I get 9. So it's a 1 to 9 ratio. So when I take the NMR, it doesn't actually tell me how many hydrogens there are. It tells me the ratio. So if I'm suspecting this might be the structure, and I know the ratio is 2 to 18 or 1 to 9, then I can look at the integrations and they confirm that. If I'm just looking at the NMR and I have no idea what the structure is, it's a little bit more challenging because I could have a structure where there's 1 hydrogen producing the signal and 9 producing this signal, or it could be 2 producing the signal and 18 producing that one, or 3 and 27. It would be difficult to imagine a structure with 27 equivalent hydrogens, but not impossible. So just wanted to point out how the integration relates to the number of hydrogens producing the signal. So we should be able to predict relative integrations if we have a structure, because we know how many hydrogens of each type are producing the signal. All right, so let's see if y'all can do this one here. So for this particular structure, you recognize that these 2 protons and these 2 protons are all equivalent, all 4 of them. There's some symmetry right down the middle of the structure right here on this axis. If you do a replacement test for any 2 of those 4 hydrogens in different combinations, you'd find by replacing one or the other, you end up finding them to be either homotopic or enantiotopic, which means they're all equivalent. Same thing for the 4 hydrogens down here. These 4 are also all equivalent. So I'd get 2 signals. We can call these A and these B. So HA versus HB. The hydrogens of type A are going to be shifted downfield a little bit from where a CH2 or methylene would normally occur. So normally a methylene comes right around the middle here, like 1 to 1.5. But because it's adjacent to a CO double bond and that oxygen is electronegative, creating a large partial positive here, that's going to de-shield and pull electrons a little bit away from those hydrogens. So the oxygen proximity isn't that close, so the effect isn't large, but typically when a carbon is 1 away from a CO double bond, we're looking at this situation here. So we're looking for it to usually appear between 2 and 3. And that proximity of a CO double bond usually adds about +1 to the shift. So it'd be fair to put those between 2 and 3 ppm. The hydrogens of type B, those hydrogens are on a carbon that's adjacent to 2 different CO double bonds. The same one that's adjacent to hydrogens A, but then this other one. So each one of those is going to add about +1. Right, so it's not necessarily as simple as just saying, okay, my hydrogen is near a CO double bond, it must be between 2 and 3. Well, that would be true if it was near 1 CO double bond. Another CO double bond on the other side also de-shields, pulls electrons away, and shifts it down 1 more ppm unit roughly. So I would expect this between 3 and 4 ppm. So if I were looking at the spectrum, I would have 1 signal between 2 and 3, and another signal between 3 and 4. And those signals would have the same area because they represent the same number of hydrogens. Their integrations would be equal. So when I sit down at the computer, I tell it to pick out this peak and give me the integration of that peak, and then I tell it to pick out the other peak and give me the integration of that. Their integration lines are going to be equal length. I won't necessarily know what the number of hydrogens are, but I'll know that they're equal. And so I can match that up with equal numbers of hydrogens of the 2 different types, giving the 2 different signals. I could set this to 1, it would put the other one at 1. Sometimes there's also little bits of impurities here and there that add or to one signal or the other, and so the exact ratio might not be exactly 1 to 1. I might find out it's like 1 to 1.1, but obviously these signals represent discrete numbers of hydrogen, so I can't have a fraction of a hydrogen. So often I might have to round here to make sure that the areas relate to a specific number of hydrogens. I could also set the signal to 4, and it would set the other signal to about 4. And that would tell me I have equal numbers of hydrogens in the structure. All right, very good job with that one. Any questions about that so far? All right, so let's talk about splitting patterns or multiplicity. So these two terms are interchangeable, they mean the exact same thing. Splitting patterns or multiplicity result when hydrogens that are not equivalent to one another interfere with each other's magnetic fields. Right, so if I had methane, like we were talking about in the beginning last time, if all the hydrogens are equivalent, they're not going to cause splitting patterns. Right? This hydrogen would potentially be split by another hydrogen on the same carbon if they were not equivalent, but because of the symmetry, and if I do a replacement test, all 4 of those hydrogens have the exact same surroundings on average. So all 4 hydrogens would give the same signal and they wouldn't cause splitting. But here in this example, we got to assume that there isn't symmetry here. So maybe there's like a chlorine over here and a fluorine over here, maybe here and here as well. Right? So this creates a situation where clearly hydrogen A, being on a carbon that's bonded to chlorines, has a different surrounding from hydrogen B being on a carbon that's bonded to fluorine. Or really any structure that creates a difference where it's not symmetrical. So A and B have different surroundings. If A and B are on adjacent carbons, or if they're on the same carbon and somehow had different surroundings. So that's, just to point that out, the situation that creates different surroundings for hydrogens on the same carbon. That occurs when I have a chiral center somewhere else in the structure. It doesn't have to be the very next carbon over, but somewhere else in the structure, if there's a chiral center here, which is now what I have, we'll just continue the chain over here. That makes hydrogen A and hydrogen B diastereotopic. Because if I were to replace one with a deuterium, I would get a different diastereomer than if I replace the other with a deuterium. And spatially, one has a different relationship spatially to the chlorine than the fluorine than the other one has. So they have different environments. That means they will potentially split one another. So hydrogens on the same carbon that are not equivalent, or hydrogens on adjacent carbons that are not equivalent, can be splitting one another. And the way that works is, if I'm looking at the signal for this hydrogen, for example, and it's got this neighboring hydrogen here, in some of the molecules, this hydrogen will be aligned, its nucleus's magnetic field will be aligned with the magnetic field of the surrounding external magnetic field of the NMR instrument. And in other molecules of the sample, this hydrogen will be aligned against the magnetic field, right? Because it's absorbed energy. They don't all absorb the energy at the exact same moment. And so some molecules, the hydrogen will absorb energy and switch its alignment against the direction of the external magnetic field. And some will maybe have already relaxed, and so they will have an alignment with the external magnetic field in other molecules. So if I've got billions and billions of these molecules at any moment in time, I've got potential for about half the molecules to have a hydrogen be aligned against the magnetic field and half to have hydrogen be aligned with the magnetic field. And whether or not hydrogen B aligns with or against the magnetic field creates a slightly different environment for hydrogen A. So molecules that have hydrogen B aligned with the magnetic field, that means that A in that molecule will absorb and release a slightly different quantity of energy than A will in this other molecule. Right? So the molecules are the same. There's no difference between them, except for that in one molecule or the other, hydrogen B is aligned with or against the magnetic field, and that creates a slightly different environment for A. So A will absorb and release slightly different quantities of energy. So I see actually two signals for hydrogen A, and that's called a doublet. It's been split from one single peak into two peaks, and one peak appears because it represents the energy released for hydrogen A in one of these molecules, and the other peak appears right next to it for the energy released from hydrogen A in the other molecules when the other neighboring hydrogen is aligned differently with respect to the external magnetic field. So we could also imagine another scenario where instead of there only being one neighboring proton of type Hb on the neighboring carbon, neighboring hydrogen A, there's two. In this case, both hydrogen B's could be aligned against the magnetic field at any given moment. Maybe one could be aligned with and the other against, or maybe this one could be against and this one could be with, or maybe they're both aligned with the magnetic field. So there's three possibilities. And the possibility where one is with and one is against is double in probability because there's two ways to do that, right? This could be up and this down, or this could be up and this down. And there's only one possible way they could both be against or both with. And so that produces a symmetrical pattern called a triplet, where the middle peak is right at the energy where this hydrogen would normally release upon being excited, because one hydrogen's alignment is with and one is against, and the energy increase for one cancels the energy decrease for the other. So the energy that hydrogen releases is the normal amount of energy it would release. But once in a while, a molecule will have both hydrogens aligned with the magnetic field, and now it will releases slightly less energy when when HA gets excited and relaxes, versus situations where both hydrogen B's are aligned against the magnetic field, in which case it takes a little bit more energy for hydrogen A to get excited, and it releases a slightly higher quantity of energy when it relaxes. So all three of these peaks result from hydrogen A, and they result from the fact that not every molecule has hydrogens B aligned in the same way with or against the external magnetic field. So if we look at this trend, what we notice is the number of hydrogens of type B splitting hydrogen A affects the number of signals I see in the pattern that results. When there's one neighboring hydrogen of type B, I get two signals. When there's two neighboring hydrogens of type B, I get three signals. Right, so that's where this n+1 rule comes from. The n+1 rule tells me that it tells me that if n equals the number of neighboring hydrogens that are splitting a certain signal like HA, that's what n is. So I just have to take that number and add 1, and that should tell me the signal, right? So if there's one neighbor, I get a 1 + 1 or a doublet. If there's two neighbors, I get 2 + 1 or a triplet. If there's three neighbors, 3 + 1 is 4. 4 + 1 is 5. 5 + 1 is 6. 6 + 1 is 7. And so these all come from applying the n+1 rule. So how do I use the n+1 rule? I look at the structure, I see how many neighboring hydrogens there are, I add 1 to that value, and that tells me the number of signals I should see in my peak. As long as two hydrogens are not equivalent, if they're on the same carbon or on adjacent carbons, they might cause splitting. And if they cause splitting, I need to add the number of neighboring hydrogens up, plus add 1, and that determines the pattern of that splitting. Just to point out, if hydrogens are 2 carbons away, that's too far to cause splitting, except when there is an aromatic ring. So you want to remember, normally only non-equivalent hydrogens on the same carbon can split, or non-equivalent hydrogens on adjacent carbons can split. So like if I had the structure here, this hydrogen we'll call A, it could split this hydrogen. And if a hydrogen is splitting one, it's also being split back. So B could split A here, A could split B, but I'd also have to look at the possibility of C not only splitting B, but also splitting A, because on an aromatic ring, we get something called long-range splitting. And this is why signals for aromatic hydrogens are often very complicated, and their splitting patterns are often difficult to determine or deconvolute because there's lots of splitting going on. It spreads out the signal. It's got this weird pattern, and often the hydrogens on a ring have similar environments, so their peaks come close together and sometimes overlap. So if I were to try to predict what the signal for this would look like, hydrogens on an aromatic ring usually come between 6 and 9. This should extend down a little bit further, but 7 and 9 is really where they most commonly come. Sometimes they come a little below 7. So if I know that it's a hydrogen on an aromatic ring, which is what we have here, I can really focus in on the area between 6 and 9. So this chlorine is a little electronegative. It might withdraw electrons a little bit, creating a little partial positive, so that will attract electrons and pull some electron density away here. So this might be a little deshielded. So if I'm between 6 and 9, I might expect hydrogen A to be a little bit deshielded around there. Just to point out, if I had just benzene with nothing on the ring, all 6 hydrogens there are equivalent, and those come at 7.26. So 7, a little above 7, is right where I'd expect to see the signal for benzene. So if hydrogen A has a little electron with density withdrawn from it by the electronegativity of the chlorine, it might be closer to 8. So I might see a signal for that. HA is going to be split by B and probably C. So if HA is here and it's split into a doublet by B, that would be split into another pair, that would be split into a pair of doublets. Talk more about that. By hydrogen C. So that would be A. If we looked at B, well, B is going to be split by A as well as by C. And B is not going to be deshielded as much by the chlorine because it's not as close. So B would probably be expected to come relatively close to where normal benzene hydrogens appear. But that's going to be split by A into a doublet. And then that pair of doublets is going to be split into another pair of doublets. So I can see those doublets might start overlapping. If 2 different signals start to overlap, then what I really get in that area is a new signal that's like larger because of that overlap, but the overlap isn't perfect, so it's probably going to be like a weird shape. So this is why I start to see multiplets appear in the area around where I normally have aromatic hydrogens, because the signals start to overlap with one another, and because there's so much splitting, including the long-range splitting, the peaks get very much kind of globbed together, and I often get something that just looks like one really jagged and complicated splitting pattern that I can't match up with any one of these symmetrical splitting patterns. And so if I don't see a symmetrical splitting pattern, I can call that a multiplet. And that usually results from lots of splitting occurring from different types of hydrogens, as well as overlapping signals sometimes. All right, so let's look at this. Let's look at this example here. We also didn't talk about this structure last time, but you may have practiced it since I put it in the lecture text thread for extra practice. So with this structure, I want to recognize some symmetry. Got a line of symmetry here. So I would expect these three hydrogens and these three hydrogens to be equivalent, right? I know that any three hydrogens on the same carbon are equivalent. So these three are definitely equivalent to one another, but if I replace one of these with the deuterium and then one of these with the deuterium, they're all equivalent because I can flip the structure over and the resulting structures would be identical, and so they're homotopic hydrogens. I also have a hydrogen here. If I replace that with the deuterium versus replacing this one with the deuterium, I would again get a pair of identical structures because of the rotational symmetry that occurs in the structure, making them equivalent. I also have this hydrogen here and this one here. Those are also rotationally equivalent, making them homotopic. If I did the replacement test, one with the deuterium versus the other, I could flip the structure over. The two structures would be identical. So those two hydrogens are equivalent. And then for the same reason, these 6 hydrogens here would be equivalent. So here I would have one signal that's orange, one purple, one blue, and one green. So 4 total signals I would expect to get in the NMR for that. So if I were trying to predict the shifts for these signals, typically a methyl group for these orange ones is going to be around 1. Is there any reason why these hydrogens on this carbon in orange would be deshielded and shifted a little bit more downfield from 1? So this is something that students often overlook. I wanted to point that out. These hydrogens here are allylic. They're on a carbon that's 1 away from a CO double bond. So when you look on the formula sheet, if you see a carbon that's 1 away from a CC double bond, the protons on that are usually going to be about 1 ppm further downfield than they would otherwise be. So normally a methyl group comes around 1. If that methyl group is adjacent to a CC double bond, it's going to come around 2. So I'll probably expect, because of these being allylic, that they would occur around 2 ppm. If I look at the purple ones, where would that signal be expected to be? Well, it's on a secondary carbon. It is a methine because there's only one hydrogen attached. So you might be tempted to say, well, if it's a methine, maybe it comes around 1.7. But if the hydrogen is directly connected to a CC double bond that's not part of an aromatic ring, I usually expect that between 4 and 6. So the purple proton here between 4 and 6 ppm. The blue is allylic to 2 different double bonds. So each allylic relationship is going to add about 1 ppm to the shift. So methylene normally comes around 1.2. It's going to be shifted down by being allylic to this double bond as well as by being allylic to that one. So each of those is going to add about 1. So probably between 3 and 4 will be the shift for those blue protons. And then the green ones, those are going to be very similar to the blue ones. Are they equivalent though? I didn't really address that. Let's take a look. So if I replace one of these orange ones with the deuterium, I would have a deuterium here. If I replace one of the green ones with the deuterium, I have it here. What's the relationship between these structures? I shouldn't put a resonance arrow there, that imply there's resonance, but what is the relationship between those two structures? They're constitutional isomers. Very good. Yeah, they are constitutional isomers. So they're not diastereomers because they're not stereoisomers. The hydrogen or the deuterium here is actually connected to a different carbon in the structure, and since there's no way to rotate this so that this carbon would be equivalent to this carbon in space, the connectivity of the atoms is different from one of these structures to the next. In order to make one structure into the other, I would have to take this deuterium off and move it to a different atom, right? So if two structures are enantiomers or diastereomers, to make one into the other, I would take an atom off and put it in a different spatial position on the same atom. But if I have to take an atom off and put it on a different atom, that means the connectivity of the structures is different. And so these structures are not identical. They're not enantiomers. So since they're constitutional isomers, or even if they were diastereomers, even though they're not, if they're constitutional isomers or diastereomers, that means those protons are not equivalent. Right? So by doing the replacement test, I find replacing one with the deuterium versus the other gives me two totally separate structures that are not enantiomers, nor are they the same. So that tells me those protons are different. So definitely, even though I would predict a similar shift for them because they're both allylic methyl groups, and I would expect this also around 2 ppm, they're not exactly the same, so they'll probably have different enough environments to shift to slightly different positions. So what would I expect the splitting patterns to be? Let's take a look at the orange one first. So I want to apply the n+1 rule. Sometimes I can't apply that, but I can in this structure. So we're just going to illustrate how to use the n+1 rule in this, and then next we'll talk about how I know when I can and can't use that rule. So to apply the n+1 rule, n is the number of hydrogens that could cause splitting. So hydrogens that are equivalent can't split one another, but hydrogens that are not equivalent to those on a neighboring carbon can split. If it were an aromatic ring, I'd look one more carbon away, but it's not, and also there's no hydrogens on the next carbon out. So normally I just look to the very next carbon over. There's one hydrogen, so n equals 1. And the n+1 rule is going to mean that I have 1 plus 1, or 2. So I expect that to give a doublet. Looking at the purple hydrogen, I'm looking at the neighboring carbon here. There's no hydrogens to cause splitting. But I got to look at the neighboring carbon over here. There are 3 hydrogens. So in this case, n equals 3. The number of hydrogens on the neighboring carbon that could potentially cause splitting, because they're not equivalent to this one that they're splitting, is 3. So I do 3 plus 1, and I get a quartet. That should be a pattern, a 4-peak pattern or quartet. Looking at the blue ones, they're equivalent to one another, so they can't split one another. But there are no hydrogens on the neighboring carbons. So there's nothing really close enough to this to cause splitting. So I'll expect a singlet. No splitting for those protons. And the same for the green. The 3 hydrogens here on this carbon are all equivalent. They can't split one another. There's no hydrogens on the neighboring carbon, so that would also give a singlet. So I should have I didn't count that out well. So actually, since there's no signals that would be above 6, let's just look at the 0 to 6 part of the spectrum. So I would expect this peak, actually let's just start on the left-hand side. So the one that had the highest ppm value, 4 to 6, that one should be a quartet. So I would expect a quartet to look something like this. The two middle signals of the quartet are usually about twice as tall as the last one. That's a little broader than normal, but I would see 4 signals for that because of the 3 neighboring hydrogens, each splitting or affecting the energy that this hydrogen releases one way or the other, depending on whether those orange hydrogens align with or against the magnetic field. I would expect to see, the next one I would expect to see would be the blue, around 3 to 4 ppm, and that was a singlet. So would that be a tall singlet or a short singlet? Well, it represents 2 protons, which is the same number of protons that the purple peak represents. So I don't necessarily know about the height of this compared to the other. It'll probably be taller because it's not split at all. But the area under the signal is going to have to be the same as the area under the purple signal, since they represent the same number of hydrogens and would have the same integration. So that signal might be a little taller, but it'll probably be a little thinner, so that the area under that signal can equal the area under this signal when it's all calculated. So then the green signal around 2 is a singlet. That represents 6 hydrogens instead of 2, so it would probably be a taller peak and a little wider, representing a larger integration. And then the the orange also represents 6 protons, but that's split into a doublet. So here it gets a little tricky. If the shift of this orange one is close enough to the shift of the green one, they might overlap. So I might not see a singlet and then a separate doublet for the other signal. They might overlap and create a multiplet in that area that integrates to a total of 3 plus 3 plus 3 plus 3, or 12 total protons, compared to the 2 of the blue type and the 2 of the purple type. But, somewhere along here I'm going to see a doublet. Oops. That's probably not great. That's terrible. Oh, man. It's so hard to draw this. It's just a doublet. There. Okay, that's a terrible doublet, but trying to show that it would have the same amount of area under it, if I color that all in and calculate the area, as the green one, since they represent the same number of protons. And again, if they're overlapping, I'm not going to see them separate. They're going to just add together in anywhere where they're overlapping. So what determines the distance between the signals when something is split? That's called the coupling constant. And the coupling constants are a way of kind of determining which signals are splitting which. Right? So if I see this orange one is split into a doublet, it's split into a doublet specifically because the purple one is splitting it. The purple is splitting the orange, and the orange is splitting the purple back into a quartet. So if the orange is split by the purple into a certain distance between the peaks, or a certain coupling constant, and the purple is split back by the orange, its coupling constant would have to be the same. So I'd have to have the same distance here that I have here. So that means I didn't really draw it very well. So whatever this distance is between those two peaks, between these two, and between those two, that should be a constant. And whatever coupling constant this hydrogen has from being split by the orange ones would have to have the same coupling constant being split by the purple one. So different splitting can create different coupling constant, but if two groups of hydrogens are splitting one another, they have to have the same coupling constant as one another. So this would have to have a distance between the peaks that's similar to the distance here. But it would also still have to have an area under the peak that's the same as the area of the green one, because both of those peaks represent 6 protons. All right, so we just did a pretty full analysis of this structure. And so let's compare that to this other structure here that we talked about on Tuesday. So let's draw in the hydrogens on this one. We said on this one there are 5 different signals. I don't need a solid or a dashed wedge on an sp2 hybridized carbon because it's flat. So I got 5 different colored protons here, 5 different signals we said last time. So how do we predict the splitting patterns here? When can we use the n+1 rule and when can we not? So the n+1 rule can be used if all the neighboring hydrogens that are doing the splitting are equivalent to one another. All right, so there are a couple details here that are really important. One is 2 hydrogens will not split each other if they're equivalent, right? So here though, because these 2 hydrogens are not equivalent, the green and blue, they will probably split one another. But since the green and the blue here have a different relationship in terms of their spatial positioning and how close they are than the blue and the red have, for example, I would probably expect, although it's hard to predict what the coupling constant will be, and I don't expect you to memorize what the coupling constants are for different types of groups splitting one another. That's way too much detail that we need to go into. But I can probably guess that the green hydrogen would be splitting the blue one with a different coupling constant from the coupling constant with which the red is splitting the blue. And so that creates a situation where I can't use the n+1 rule. All right, so let's go through and illustrate this at an example. So over here, it's a little bit more straightforward. We'll call this hydrogen A, for example. This one will be split by the purple one, right? There's no other hydrogen close enough. There's no hydrogen on this carbon. And these other ones over here are too far away to cause splitting. So B would be splitting A. And there I can apply the n+1 rule because all the hydrogens splitting A are equivalent to one another. There's only one. So if there's only one neighboring proton, the n+1 rule is going to apply. So n equals 1, 1 plus 1 equals 2, and I expect HA to be a doublet. Oops, well, I can't move that. All right, so that's HA. HA is split by B into a doublet. That's the only proton here that I can use the n+1 rule to look at. So let's look at B. What's the splitting pattern for B? If I try to use the n+1 rule, I'm probably not going to get the pattern correct. Because applying the n+1 rule here, I would look at how many hydrogens there are on neighboring carbons. So there's 1 here. This one is neighboring here, so this would split, that's 2. This will split, that's 3. So I would get a 3 plus 1 and expect to see a quartet. In reality, I'm not going to probably see a quartet for B because in order to see a quartet, HA, HC, and HD would all have to split B with the same coupling constant. Right, so just to contrast that with what we said over here, for this hydrogen here, these 3 hydrogens are all equivalent to one another. They're on the same carbon. They're all homotopic. All three of these green hydrogens are equivalent. So they're all splitting this one over here with the same coupling constant. And when the coupling constant is the same, that's when I can apply the n+1 rule. So that's why I was able to predict a quartet for this proton, split by 3 equivalent protons, all 3 splitting with the same coupling constant, creating a symmetrical pattern where the coupling constant is the same distance between the peaks here as it is here as it is here. Right, this distance between the peaks. But down here, since hydrogen B is split by A, and A is very different from C and D, C and D are also different from one another, the odds that all 3 of those protons would be all splitting with the same coupling constant to produce a quartet like we saw here are very low. So it's possible I would see a quartet. It's always possible that the n+1 rule could give the correct splitting pattern. But I want to be aware that when the neighboring hydrogens are not equivalent to one another, meaning A and C and D are not equivalent to each other, I don't expect them all to split B with the same coupling constant most of the time. So the pattern for B is going to be more complicated than that. If I've got more than 2 different types of hydrogen splitting, each splitting with a different coupling constant, that's going to get more complicated than I expect you to be able to predict. So you could just call that a multiplet. So I would probably see a doublet for HA and a multiplet for HB. If they're shifted to a similar spot, since they have similar environments, they might overlap and create one big multiplet that integrates to 2. So I want to be aware of the possibility of peaks overlapping as well. All right, let's take a look at F. Well, the coupling this is supposed to be E. I don't know why I skipped a letter there. Let's take a look at HE. Its coupling constant. So there's nothing on this neighboring carbon to split it, but C and D should both split. Now C and D here are pretty similar. They're on the same carbon. They're diastereotopic though, so they're not equivalent. So they may not split E with the same coupling constant. Right? So what I can say here is if HC and HD both split HE with the same coupling constant, which is symbolized with a capital J, then I would get a triplet because there'd be I could apply the n+1 rule, which would give me a triplet. But if HC splits HE with a different coupling constant, then HD splits HE, I'm not going to get a triplet. What am I going to get? Well, let's explore that a little bit. So it depends on the sizes of the coupling constant. So let's say the coupling constant, let's just give a hypothetical. So let's say the coupling constant for C coupling E is large, just for the sake of argument, and that the coupling constant for D splitting E is small. One is probably going to be larger than the other. We don't know which is large, which is small. But if one is larger than the other, here's what you're going to see. So in this scenario, E is going to be split by C into a large coupling constant. So that means the distance between the signals is large. There's a large distance in ppm between the signals because they're split with a large coupling constant spread out a greater distance from one another. So this is what I would get if C is splitting E. C would split E into a doublet. But then D is also splitting E. So D splits those doublets into doublets. So instead of seeing 2 single peaks at that distance, the peak I have here is going to be split into a doublet. And peak over here is going to be split into a doublet. So here I had a doublet that was split into more doublets. I have the larger coupling constant between these two doublets because of the large coupling constant between C and E. And then I have a smaller coupling constant between the second splitting for D splitting E. So that's called a doublet of doublets. Questions about that? All right, let's see if you guys can do one. See if you can predict the splitting patterns for this structure despite the n+1 rule not necessarily applying to every proton in the structure. All right, I'm not going to go back and say all that again. Sorry about that. I didn't record it. Thank you for pointing that out. For E, it's going to be split by D. That's the only neighboring proton to E. Everything else is too far away. So if there's one proton, 1 plus 1 gives me 2. I expect a doublet. HF. F is going to be pretty complex. F is split by G. Any proton on the same carbon that's not equivalent, these two happen to be diastereotopic, so they're not equivalent, will cause a splitting. D is also on the neighboring carbon. It's going to split F. E is too far away, so I don't have to worry about E splitting F. But H is right on the next carbon. H is going to split F. So the hydrogens of type H, there are 3 of those. So 3 plus 1 is 4. That means hydrogens of type H are going to split F into a quartet. G would split F into a doublet. And D would split F into a doublet. So I might have a doublet of doublets of quartets, or a quartet of doublets, right? That's going to be more complicated than I expect you to draw, though. So again, if there are 3 different types of hydrogens causing splitting, we can call that a multiplet. Same thing for G. It's going to be split by F and H and D into a very complex splitting pattern. And then finally for H, H is more simple. It's only split by 2 protons on the neighboring carbon. So if F splits H with the same coupling constant that G splits H, so we can say if HF and HG split HH with the same coupling constant, then it'll be a triplet because n plus 1 is going to be 2 plus 1. But I want to also be aware I may not see a triplet because F and G are not equivalent. They may split H with significantly different coupling constants. F would split H into a doublet, and G would split H into a different doublet. So a doublet of doublets, which again looks something like this, right? One splitting at one distance, and then another splitting of that into a shorter distance, depending on which coupling constant's larger, and which coupling constant's smaller. So I like this question from the textbook relating to what we just talked about. So I pulled it over here, looking at the protons on the styrene. So we're not looking at the ring right now. We're just looking at the protons outside the ring here. All 3 of these would be expected to come between 4 and 6 because they're on an alkene. But this question gives us the coupling constants. It says A is splitting B with a coupling constant of 11 hertz. C is splitting A with a coupling constant of 17. and B is splitting C with a coupling constant of 1. And coupling constants go both ways. So if B is splitting C with a coupling constant of 1, C is splitting B with a coupling constant of 1. That means the distance between the peaks is short versus the larger distances over here. Right? So what would the splitting patterns be expected to be? Well, if we looked at HA, it's going to be split by B into a doublet. It's going to be split by C into a doublet. The coupling constant here is larger than this one. So I would have, first, C would be splitting A into 2 signals at a distance of 17 hertz. But then those signals are also split by B splitting A with the coupling constants of 11, which is not exactly half of 17, but it's smaller. So this one is going to be split into a doublet with a coupling constant of 11 hertz. And this one here is going to be split into a coupling constant with 11 hertz. And so I just wanted to point out with some numbers how the shapes of the signals result. So let's just look at C. And B and C are going to be real similar. So for C, if I look at the pattern, C is split by A with a very large coupling constant. So again, the signals would be separated by a distance of 17 hertz. But then C is split by B with a much smaller coupling constant. So that means these two signals now are going to be much closer together. So there'd be a distance of 1 hertz there between the second splitting of that double split signal, or doublet of doublets. Right, so just to point out, the peaks can be wider apart if the coupling constant's larger, or they can be closer together if the coupling constant's shorter. But typically, protons that have different environments will split one another, at least with some kind of coupling constant. Also wanted to emphasize something in the textbook. Typically, we see some of these common patterns, so I wanted to point those out. So if I have an ethyl group, what results with an ethyl group typically, assuming that there's nothing over here to cause splitting, and that the only splitting for these two protons comes from these three, these three would all be equivalent, and so these would be splitting 3 plus 1 into a quartet. I would see a quartet for this signal. Let's see exactly what I see. A quartet with an integration of 2, because there are 2 protons producing a signal. They're split into a quartet by the 3 neighboring protons. For this signal, it has an integration of 3, because there are 3 protons of that type. It's split by 2 plus 1 into a triplet. And that's exactly what I see, a triplet there with an integration of 3. So if you see a triplet and a quartet, and you see that the coupling constants are the same, or that the distance between the peaks here is the same as the distance between the peaks here, at least by eyeballing it, that's an indication of the presence of an ethyl group, because they're splitting one another into these exact triplet and quartet patterns with the integrations that match the number of hydrogens on each carbon there. If I have an isopropyl group, we'll draw that down here. So let's assume whatever X is, it's not going to cause splitting. So this proton here is going to be split by 1, 2, 3, 4, 5, 6 equivalent protons. Right? Every one of these green protons is splitting the black one. But they're all equivalent. All the green ones are equivalent. So they're all splitting the black one with the same coupling constant. And that's when I can use the n+1 rule. So I have 6 protons of that type. Gives me a septet. And that's what I see here. I count 1, 2, 3, 4, 5, 6, 7. 7 signals in a symmetrical splitting is a septet, and that occurs often for an isopropyl group because there's one proton being split by 6 equivalent ones. If this proton's being split by those 6 with this specific distance or coupling constant between the peaks, then, which, is very small distance, then the other hydrogen has to be split by those 6 with this, the other 6 hydrogens have to be split by this one proton with the same coupling constant. So it's splitting every one of those 6, but all 6 of those are equivalent, so they all give the same signal. So it's splitting this into a doublet, splitting this into a doublet. It's splitting every one of those into a doublet, but I only see one doublet because all 6 of these are equivalent and they all give a doublet in the same spot. But that doublet, because there are 6 hydrogens, has an area in its signal 6 times the area of the other signal. This is just a signal expanded so you can see how many peaks there are. And then a terp butyl group, even if this had protons on it, whatever, a terp butyl group has a carbon with no hydrogens. And then it's got 9 equivalent protons because of the rotational symmetry. All 9 of these protons are equivalent. So when you see a big tall singlet that integrates to 9 compared to any other protons in the structure, that's a good sign of a terp butyl because that's how you get 9 equivalent protons all giving the same signal with no splitting because there's no hydrogens here on this carbon since it already has 4 bonds. And so hopefully those examples help you with splitting. Another important point from this section of the textbook is that aldehyde protons, so here's an aldehyde, and alcohol protons, here's an alcohol proton is an OH, often don't cause splitting, or they have really small coupling constants, so you don't see the splitting that results in those structures usually. And so what we're saying here is, what would I expect the splitting patterns to be here? Well, if I were just using the n+1 rule, I'll expect these 3 protons to split this into a 3+1 or a quartet. And I would expect this one proton to split those into a 1+1 or a doublet. So I might see, for these hydrogens, I might see a doublet of quartets or a quartet of doublets. But since this is an aldehyde proton, which means it's directly connected to a CO double bond carbon, the coupling constant's probably too small. It might not even be significant enough to cause a measurable splitting. So I'll probably just see a quartet for these protons instead of doublet of quartet or quartet of doublets because the aldehyde splitting would be minimal. Same thing here. This proton here could cause splitting on these hydrogens. And with an alcohol, sometimes I see it, sometimes I don't. Also with an aldehyde, sometimes you see the splitting, sometimes you don't. So it's a little bit hard to know for sure, but at least you want to be aware of what you might see. And so for these 2 protons, they'd be split by these 2 neighboring protons, assuming there's no chiral center. These 2 would be enantiotopic, they'd be equivalent. And so since they're equivalent, I can apply the n+1 rule. These 2 should split these 2 on the neighboring carbon, 2+1, into a triplet. This one, since it's on an adjacent atom, should also cause splitting, 1+1, into a doublet. So for these 2 hydrogens, I might see a doublet of triplets or a triplet of doublets. Or since this proton is on a hydrogen, it makes it exchangeable. It might be exchanged with the deuterium from the solvent, so I might not see a signal for this proton at all. Or it might just be involved in hydrogen bonding and replaced with other protons and shuttled back and forth with some trace amount of acid that's present, in which case it's not around long enough to cause splitting, so I might not even see that splitting. So for these 2 hydrogens, the signal I might see, it could just be a triplet, or it could be a triplet of doublets or a doublet of triplets. By the way, what's the difference between a triplet of doublets versus a doublet of triplets? Well, it's exactly what the words are saying. A triplet of doublets means you have 3 doublets. So that would be a doublet, 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 right? So it's like a triplet, but it's a triplet of doublets. A doublet of triplets would be like a triplet, but each peak is split into two, a doublet of triplets. Oh no, that's what I just did. A doublet of triplets is where I have two triplets. So one triplet, and then I get a doublet or two triplets. So I would have something like this. Let me do that again. So here I have a triplet of doublets, here I have a doublet of triplets. And I get the doublet of triplets if the coupling constant that's causing the triplet is larger than the coupling constant causing the doublets. Here the coupling constant causing the triplets is smaller than the coupling constant causing the doublets. So you want to be aware of those options as well. All right, so I was hoping to have time to practice some of these types of questions where I give you different spectral information, expect you to draw a structure. These are challenging, they're kind of like a puzzle, but you can get a lot better at them the more you practice. But unfortunately, we ran out of time on that. So I'm just going to post these up in the lecture test thread if you want to practice them. Send me your work on these. These are also among the questions I assigned for you to practice. So you can also look at those in the textbook, but I know that we focused most of our time on looking at structures and trying to predict what the signals would look like, because that's like the foundation of this. But you also want to be able to look at an NMR with the signals and start to piece together what the structure might look like. So you want to practice both types of questions where you're either given a structure and expected to predict a spectra, or given the spectra and expected to draw a structure that could plausibly have produced that spectra. Right, so actually, I'm just going to go through this one. If you have to go, since we're out of time, feel free. But I did want to just explain kind of like the strategy for how to do one of these real quick. All right, so there's some information given in this question. We want to draw a bond-line structure that matches the spectra that we have here. And we want to predict the diagnostic IR signals and what the N+1 and molecular ion signal might be. All right, so the first thing I'd want to do here, if I have an NMR signal, look at the integrations. Those tell me how many hydrogens are producing each signal. I'll look at the splitting patterns, look at where the shift is. So probably I would start with the shift in the integration. Right, so here I've got a peak that's between 1 and 2. So that limits what's happening. And this signal represents 9 protons. So that's probably a terp butyl group like we were just talking about. Typically, to get 9 protons that are all equivalent and give the same signal with no splitting, I've got to have a terp butyl group. Right? So the way you want to approach these, it is a lot like a puzzle, right? When you put together a puzzle, you have all the individual pieces. You got to see how they stick together. Well, here we don't have the pieces. So the first thing we want to do is start by creating pieces of the structure and then figure out how they fit together to give the right splitting pattern. So one piece is going to be this terp butyl group. It's going to be bonded. We don't know what to what. But this carbon here doesn't have any protons. So all 9 protons on these 3 methyl groups are equivalent, and they're not causing any or experiencing any splitting, so they're going to be giving a singlet. And there's nothing highly electronegative near them, so that's why the singlet comes roughly around 1. All right, so what else do I have here? I've got the signal down here around 7, and that's usually an indication of an aromatic ring. So here's another piece of my puzzle. I'm going to have an aromatic ring present here. And the protons that are directly connected to the ring look like they add up to a total of 4 protons. So if I have 4 protons on the ring, I have to consider, are the protons all next to one another and then the things that are substituted are there and there? Or do I have maybe the 4 protons in these positions and the 2 groups attached are here and here? Or one other possibility, maybe the 2 groups attached are here and here, and the 4 protons are like this. And so from the splitting pattern, can I tell which piece of the puzzle I probably have? Sure. in this situation here, there is probably some degree of symmetry, but this hydrogen is unique. Well, it would, depending on what these groups are, it might be equivalent to this one, but it would definitely be split by, probably due to the long range splitting on aromatic rings, split by this and potentially by that one. For sure, though, in this structure, if I were to look at how many protons it would give me, even if these two groups were the same, I would expect to see 3 signals, and really I only see 2 there. Same thing here, even if these two groups were identical groups, and I had a line of symmetry, actually if they were identical groups, then I would only get 2 signals, so that's hard to tell for sure. Here though, even if the groups were different, I would get 2 signals there because of, now I've got symmetry here. So these two would be equivalent and those two would be equivalent. I don't expect the groups in my ring to be the same group though, right? So, if I imagine this was X and this was X, if they were the same, due to the symmetry here, these two would be equivalent, these two would be equivalent, I would get 2 signals. But I think one of my groups is a terp-butyl group based on this signal. And so I probably don't have 2 terp-butyl groups, otherwise I would have an integration of twice that integration for the amount of hydrogens on the ring. And I also have this signal here. It's kind of a broad singlet.
Wouldn't H like have narrow compartments?
Which, you're talking about this proton here, HB? So HB would be split, it can't be split by another equivalent proton. Equivalent protons don't split one another. So it'd be split by A, and it would probably be split by the other A through long range splitting. So that might be 2 plus 1, it might give a triplet. So that's a good point. So having 2 protons of the same type splitting it with probably this potentially the same coupling constant, that could give a triplet. Or if these two A's split with different coupling constants because they're not splitting from the same distance, I might see a doublet of doublets for HB. So this kind of looks like a doublet of doublets, but then I would, I'd still need to see a signal for HA somewhere, and it wouldn't be accounted for if this signal were only for HB. So that's a really good point, and that really does pretty much rule out this as a possibility. And we already ruled this one out as a possibility given the number of signals. So this definitely seems to be the puzzle piece we have, because in this situation, in terms of the splitting, which I didn't really even get to before Austin mentioned it, but that was an excellent point. HA is going to be splitting B. There's nothing here to split it if there's another group attached. There's no proton there. This one over here can't split it because they're equivalent. The 2 B's are equivalent to one another. And this one's too far away. So this A would be splitting B into a doublet, and that could account for one of these doublets. And then B would be splitting A back into a doublet, and that could account for the other doublet. So this particular configuration or connectivity for the atoms, assuming that X and Y are different from one another, if they're the same, all 4 protons would be equivalent on the ring, and I would have a singlet for all 4 of them. But assuming that they're different groups, that would make A and B non-equivalent to one another, and so they'd be splitting each other into doublets. So that definitely seems to make sense. Great point. So back to the signal around 5 that integrates to 1. A broad singlet usually is an indication of an OH group. Just like in the IR, if the oxygen-hydrogen bond is weakened by hydrogen bonding, and that's not happening to the same extent on every single molecule, then not every one of these hydrogens is going to have the exact same environment at every moment. And so I see a broader signal here instead of a sharp, narrow signal suggesting all the hydrogens have the exact same environment. There's ones that have slightly higher energy, ones that have slightly lower energy. So I see this broad signal produced by all those individual signals for the molecules, not all having the exact same environment. So that's usually an indication of an OH. So now I just have to put this together. So I have an OH piece, I have a terbutyl piece, and I have this aromatic ring piece. Once I have all the puzzle pieces, there's usually only a couple ways to fit things together. Let's move this out of the way. So this is probably the best structure I can draw from that proton NMR. I put a terbutyl group on one end and an OH on the other end. Then I want to make sure I can assign the protons, right? So this signal I could call A, and that would represent all the protons, all 9 protons on the terbutyl group. I would expect to get an integration of A with a singlet coming around 1 ppm. For the protons that are here and the protons that are here, those produce the 2 aromatic signals. We don't have to get into too much about why B and C aren't in the exact same spot and why one is further downfield than the other. But 2 protons integrating into 2 of type B, 2 protons integrating into 2 of type C. Splitting each other into doublets gives me a pair of doublets. 1 doublet for B, 1 doublet for C, both integrating 2 because they both represent 2 protons. And then the single proton with integration of 1 on the OH group could be the signal at around 5. Once I have the structure drawn, I should also be able to predict where the IR signals are. So I would have a broad stretching signal around 3500 in the IR for the OH. I would have some CH stretching on sp2 hybridized carbons around 3100. And I would have some CH stretching on sp3 hybridized carbons around 2900. Those would be the signals I'd expect to see. I might also see a carbon-carbon stretching, a CC double bond, around 15 to 1600, but I might not see that if the bond is not very polar. So that might be a small signal. I might overlook it, but I would definitely look for the other ones there in the IR. And then for the molecular ion peak, the molecular ion is the signal I get in the mass spec when there's a carbon-12 in every atom. So I'd add 12 for each carbon, 16 for the oxygen, 1 for each hydrogen, and that would give me the mass of the molecular ion. The M+1 peak occurs when a few of the structures have a carbon-13 incorporated into them. So it has 1 mass unit more than the molecular ion peak. And since carbon-13 is a 1.1% natural abundance compared to carbon-12 with a 99.9 or 98.9% abundance, if there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total carbons, then there's a 10 times 1.1 or 11% chance that any one of those carbons could be a carbon-13. And so that means the peak that's 1 mass unit larger than the molecular ion peak should be 11% as tall as the molecular ion peak. And so it's just a little review from the mass spec and IR content we talked about that will be on your exam next week. All right, so I'll put this one up in the lecture text thread if you want to practice it. Any questions about anything before we end?